Yes. Hello again, and thanks for coming. Thank you to all of our attendees and to all of the people who are watching us through internet. So now we will proceed with our schedule. We welcome to the stage Dr. Shurmin and Evgenia Krylova from Kaspersky, who will perform a talk about the usage of steganography by Epi team and general malware. So an applause, please, and we will begin with the talks.
Olá, boa tarde, como estão? Am dic Eugenia Krylova, trabalho aos laboratórios Kaspersky. Hello, ladies and gentlemen. My name is Evgenia Krylova. This is Alexey Shulmin. We are from anti-malware team, Kaspersky Lab.
Yeah, and a few words about us.
Let's start from me. I work in Kaspersky for 7 years, and I started my career as malware analyst. And last year, I'm a manager of Shift Malware Analyst Group, but I tried to continue my research. My research is different for different conferences. My specialization is network traffic detection. And by different intrusion detection systems like Suricata or Snort. That's all about my work. What about my private life? I'm a wife, I'm a mother. I'm a wife, I'm a mother, and my hobby is baking cakes.
Like that one?
That's my cake, yes.
Well, a few words about me. I'm targeted attacks research team lead in Kaspersky Lab. My professional area is the discovering new complicated APTs and researching them as deep as I can. I'm researcher, speaker, programmer, security enthusiast. And my hobby is my work. I do love my work.
Me too. Okay, steganography exists for many centuries. And what is steganography? Do you know? Raise your hand if yes. Okay, briefly, steganography is about how to hide not only the information for transferring to another people or anything else, but for the hiding the channel of transferring. As I already said, steganography exists for many centuries, and I bet many of you remember the story about the shaved head of a bondman. Yes? No? Oh, this story is about how to hide secret information in ancient Rome by making tattoo on the shaved head of a bondman, and after hair grew, he must go to another place and transfer this information such weird way. That's steganography in ancient Rome.
Yeah, and by the way, this picture was especially created for our presentation because I was trying to find the appropriate picture on the internet, but I failed because our domestic local search engine, Yandex, it's Russian Google, by my request, slave's shaved head, showed me that one. Policeman in Russia.
Yes, that's about Russian policemen and about steganography in ancient Rome, but what about steganography nowadays? Nowadays we can see that more and more advanced persistent threats and malicious families use steganography for transferring data or payload or different comments to command and control center and to infected machine, back and forth, back and forth. For example, last year we discovered advanced persistent threat 0T that uses steganography for transferring malicious payload to infected machine. Not only advanced persistent threats, but even ordinary malware use steganography for delivering any content. For example, such Trojan bankers as Fitbit, Kins, and Sberb use steganography too, and many other different malicious family use steganography also.
So why do malicious authors decide to use steganography? I know at least 3 reasons for it. First of all, the usage of steganography allows them to hide downloading process itself, not only the data. Then it's also possible to bypass DPI solutions due to legitimate traffic. I know that it's very weird, but I can remember at least one story about one internet service provider in Russia who decided to block all objects in traffic that weren't recognized by their DPI solution. It's really weird because they blocked also all encrypted traffic like HTTPS and so on, but they did it, I don't know why. And the third reason, the usage of steganography allows the bad guys to bypass anti-APT products in security service, because of the performance issues. It's absolutely impossible to process all files that can be a container in traffic.
Okay, meet Lena. Can you see any differences between these two bitmap files? No, me too, but there is at least one. We have hidden 10 parts of Lolita novel by Vladimir Nabokov into the right image. But the size of such 2 images is equal. This is LSB steganography, least significant bit steganography. By the way, Lena is a popular image for different tests by graphical researchers. And Lena Soderbergh is actually a Playboy model from 1978. And let's take a look at the original image of her. Yes.
So what we are going to talk about? I'm going to tell you about different steganography methods like LSB method. LSB here stands for the least significant bit, about the obsolete steganography method overlay steganography, and about DNS tunneling. Well, actually, researchers don't associate DNS tunneling and steganography, but we do, because we're sure that it's actually the same thing. Also, I'll tell you about methods of detection, how to understand if this file is a field container or not. I'll tell you a story about visual attacks and about statistical methods and about exact methods and idea systems. And if it's possible, I'll show you a live demo. I'll show you how to hide information in container and how to understand if this is a hidden message in this file or not.
Okay, let's start with LSB steganography, least significant bit steganography. We can say that it is true steganography because, as I already said, for the image after embedding the data, the size of this image will be equal with the original size, with the size of original image, sorry. And
this is an example. As Evgeny already told you, last year we discovered an APT downloader. We called it 0T, but it was described by our colleague, as far as I can remember, from Proofpoint. So this malicious downloader gathers information about the operating system, sends it to its own command and control server, and downloads 3 bitmaps, Forrest Gump poster, Britney photo, and Stevie photo. But actually, all these files are field containers, and after processing them, the malware gets its models extracted. So the question is how to understand if this graphic file, for example, is a field container or not. It's very easy by using the visual attack. So we can construct a new image from the original one from the least significant bits of every byte. For example, the second picture was constructed from the original Stevie photo from previous slide by using only the least significant bits of every byte of red color channel. And the last picture was constructed by using the least significant byte of the least significant bits, of every byte of each color channel. And as you can see here, there are at least 2 areas with high entropy, and it means that there's something here. It means that this file is a field container. As you can understand, this method is good for manual research, but it's absolutely inapplicable for automatic detection because, as you can understand, there's no dedicated analyst in anti-APT products. We have absolutely no time to construct new images, blah, 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 to inspect them and so on. So we need something for understanding in fully automatic mode if this file is a field container or not. So there are at least two methods. We call them statistical methods because they based on math statistics, and the first one was called?
The first statistical method is the histogram method or chi-square method. This method was invented almost 20 years ago in 2000 by Andreas Westfeld and Andreas Fitzmann. This method is based on the assumption that for two neighboring colors with a difference only in one bit, least significant bit, the number of pixels into the image for each of such neighboring colors will be similar or equal. Such distribution you can see on the right part of this slide. So we have 4 pairs of neighboring colors, and the number of pixels is equal. In the left part of this image, we can see the distribution for the empty container without any embedded data, and the number of pixels for neighboring colors is really different, significantly different. This method has a lot of different formulas, and this is a piece from the original paper. But what you should know. You should know that after calculating all these formulas, we should get only one value, chi-square value. And we should calculate this value for each piece of our image, that we should divide this image into 10 pieces, for example. And we should take a look at these chi-square values, and if we have significantly different two neighboring chi-square values, we can say that this is image with embedded data. Let's take a look on the real example. We have taken the original image with this pretty girl, and after applying visual attack, we can that there are no areas with any high entropy, and we have divided this image into 10 slices and calculated chi-square value for each of such sections. And let's take a look at the chi-square values. We can see that there are no two neighboring values with the difference more than 2 times. Okay, then we have embedded encrypted payload into this image, and let's take a look at the visual attack. We have a big part with high entropy. And after calculating chi-square values, we can see that at least 5 sections, from 5th till 9th, we have chi-square values really lower than in another parts of this image. So we can say that this image is full with embedded data, and it's true.
So the next method we implemented and tested, called RS method. RS here stands for regular and singular. It was invented almost 16 years ago, and this is a mathematical base of this method, but actually it's very difficult for me to explain how does it work, but I can try. So the whole image is divided to a set of groups, and for each group the flipping function is applied. According to a value of the special discriminant function before and after flipping, all groups are divided to regular, singular, and unused. And this algorithm is based on the assumption that the number of regular groups and singular groups of pixels in original and flipped images should be almost equal if this image is an empty container. And if they are significantly different, that means that this container is filled. So let's check this method too. You can use the same pictures. As you can see here, for the first test case, this attack told us that less than 1% of the image is filled. And it's true because it's an empty container. You can see there's nothing in it. There's no area with high entropy. And for the first test case, More than half of the image is filled, and RS attack told us that 44% of the original image is filled. And it's true, but both methods, chi-square attack and RS attack, rely on the assumption that the embedded data has high entropy. But in the real-world example, for example, in 0T example, all embedded data has ordinary entropy. And the question is, will these methods be able to detect the embedded data, the field containers, in case when the embedded data has ordinary entropy? Let's find it out.
Oh my gosh, Brittany again. I suppose, Alexei, you are in love with Brittany?
No, definitely not, but I'm sure that memory offers this.
Okay, let's check both methods on the real APT Stego containers. And for the first Brittany, chi-square attack unfortunately failed. And we see that there are no large differences between the values. But surprisingly, RS attack gave us good result. And we can find out that according to results, 60% of image is filled by another data, and it's true.
So for the next Brittany, chi-square attack gave us uncertain results, but RS attack told us that at least 15% of this container is filled. So actually for the RS attack, we should set the border of accuracy, and we decided that 10% is a good border of accuracy. So if RS attack tells us that more than 10% of this image is filled, so we can trust, we can rely on these results. But what should we do if both methods are failed or gave us uncertain results, but we are still sure that this container is filled? For example, like here, we can apply the exact extracting procedure. This is a picture from the real life, from the real world. It was used by 0T malware. This is my script for extracting the data from the least significant bits, and as a result, we have got the payload. It's executable files malware.
Okay, let's move on to another steganography type, overlay steganography. This is, we cannot say that it is a true steganography because the size of the container after embedding will be bigger. Alexei, please.
Oh, sorry.
Okay, let's take a look at this picture. Alexei, how do you think? Is it picture suspicious or not?
Well, actually, I can't say anything suspicious here, but I'm sure that this picture is a field container because I can't believe that you inserted this picture in our presentation just for fun.
Yes, you're absolutely right. And this is a Stego container with embedded data in overlay. Please. Okay, let's take a look at the dump of network traffic of this malware. This is SBERP. SBERP is a malware, some kind of mix of Z-board and CARBERP. Maybe you know such Trojan bankers. What can we see on this slide? We can see the transferring of JPEG file. Yes, as a snort analyst, I can distinguish suspicious traffic even without TCP session assembly. But if you see JPEG transferring, is it suspicious? No, it's really boring. But if we scroll down our traffic to the bottom of the assembled session, we can find out weird base64 string that is really unusual for JPEG file format. This is overlay steganography, and under base64 encryption, we can find the encrypted configuration file of this malware, where we can find the list of targeted banks. So how to detect?
So they thought that it's very easy to detect overlay steganography. All that we need is just to calculate the size of the original file and check if this is something here, and if so, then detect default. So we implemented this logic. We have created a lot of signatures. We published them. And as a result, we have got a huge amount of false alarms. It absolutely doesn't work this way. So, but what should we do to make a proper detection of overlay steganography? First, we should check that the file starts with a correct header. We should use all information from information fields from header. We should act like a real viewer. We should consider the length of overlay, and we should consider and overlay entropy should be high enough, and it should be significantly different from the entropy of the original file. And of course, we should check if the overlay starts with the well-known signatures like PK, for example, and if so, then detect it.
What are another methods of detection overlay steganography? Of course, we can detect it by network traffic, by intercepting network traffic and detect it by different intrusion detection systems like Suricata or Snort. Let's no, Alexei, please. Okay, we can try to create a Snort rule right now for this SBERP malware. First of all, we can, first of all, we should make sure that it is really JPEG transferring, so we should find the real JPEG file format extension. And as you may know, JFIF file format consists from different markers or marker sequences. For example, FFD8 is a start image marker. And where can we hide the information? For example, configuration file in the comment section of JPEG file. Please. Okay, yes, and FFFE is a marker of the beginning of the comment section. And for this malware, we know that the next bytes, 3F and 10, this is the length of section of comments. And you can find that this is a huge number. And this number is hard-coded into this malware, and in each traffic that we saw, this marker is I equals. So we should create a signature on this hard-coded bytes after FFFE markers. And then we should make sure that our base 64 string goes to the end of the image. FFD9 is marker of the end of the image. So this is our Snort rule. There are two rules. This is a chain of rules. In the first rule, we can see JPEG extension, and then we can find in the next rule hard-coded bytes with the marker of comment section and hard-coded value. And then PCRE with the end of comment section. That's about Snort.
Another type of steganography, DNS tunneling. Actually, this is not our topic. It's a topic of a researcher, Sergei Yanakovsky, our colleague. He will tell you a bit more about this kind of steganography just right after us, but I can explain how does it work. So let's say that this computer in a corporate network is infected by APT, for example, and this APT needs to exfiltrate stolen data from the corporate network. It sends a DNS request blah blah blah.badguy.com to the internal DNS server, but the internal DNS server can't resolve this request because this server doesn't know anything about blah blah blah.badguy.com and about badguy.com. So it has to forward this request to the external DNS server here. But this server, external DNS server, also doesn't know anything about badguy.com. And actually, there is only one named server in the internet who knows something about badguy.com, who can resolve this request. And this server is controlled by a bad guy. So a bad guy gets this request, extracts data from the first part, and it can send the response with, for example, with command to APT or something like that. It's easy. Live demo. As I've promised you before, I'm going to show you how to embed data into container and how to understand if this container is filled or not. Check, check, check. So we need some tools. We need my detection script. We need Python, because my detection script, my detection logic is implemented as Python. Luckily for us, I've installed Python yesterday. Oh, sorry, this is a picture for the next test case. Also, we need a program to embed data into a container. This program is called an implant. Oh, sorry. Wait a minute, please. We have some technical problems. Well, now it's fine. Looks fine. So we're going to embed Hamlet play, Hamlet novel into the container, and the container is here. It's Evgenia's photo. So again, I have to do it. We need a program to embed the data. For example, I like very old program in plain view. It was created, as far as I can remember, in 1985, but it works well enough. It implements USB steganography, and we need something to make a visual attack on the picture. We have simple Java program. So let's open our original bitmap, our original Evgenia's photo here. This is the original Evgenia's photo. And let's apply chi-square attack. Let's construct a new image from the least significant bits of every byte of each color channel. Well, what can we see here? Well, actually nothing. There's nothing in it.
No Evgenia. Yes?
And there's no area with high entropy, because this is the original photo. And now let's apply both attacks. I mean chi-square attack and RS attack to the original photo. So we just need to run my script. What can we see here? 10 sections and chi-square value for 10 sections, and they are different enough, but they are almost equal. It's so we can say, according to these results, that this container is probably empty. Now my script is working on RS attack. It takes time because it's very complicated attack, and while my script is thinking, I'll show you how to embed the data into this container. We have a program in plain view. Let's select our original file. Let's select Hamlet play, and we should type here the name of the output file. Let's say, for example,
Zhenya 2.
How?
Stego is already here.
Stego doesn't matter. Stego, let's say Stego new, because we already have Stego BMP. And I want to set a password. I want to protect my Hamlet play with a password, very complicated password, 1, 2, 3, 3, 2, 1. Okay, let's do it.
what happens? Now we have a new file called StigoNew. So this is the original EGS photo, and this is a photo, and this is a photo with embedded data. Can you see the difference? This is what I can show here. Oh, sorry. This is the original photo, and this is a photo with hammer play embedded. I can't see any difference, but maybe I'm blind, but I suppose you can't see any difference too. And here are results for the RS attack. As you can see, as you can see here, our RS attack told us that for red plane, less than 1% is filled, for green plane, less than 1% is filled, and the same for the blue plane. And it means that this container is empty. So now let's try to apply my script to the filled container. StigoNew. What we can see here, you can see that for sections from 3 to 9, we have a huge values of chi-square distribution. And while my script is thinking, I'm going to show you the visual attack on this image. Let's open field container here, StigoNew. It's the EGS photo again, as you can remember. And let's apply visual attack to it. As you can see here, there is a huge area with high entropy. Our hamlet play is here. And now we have results of the RS attack for red plane. Our script told us that 80% of the red plane is filled, and it's true. Now we have to wait a bit more.
We can dance.
Oh, this is a good idea.
Results for green plane, 76% is filled. And we are waiting for the last one, for blue plane. Sorry, I promised to optimize my script. Because I had only one aim. My name was to implement the detection algorithm as precisely as I could. So, we have results. Our attack told us that 78% of the original image is filled. And that's true. Evgeny, I'm tired.
Okay.
Please.
That's my turn. Okay. Whoop. My mission is to extract a payload from Britney. Yes. Take a look. This is the image from 0T APT downloader. Alexei, where is your tool with the visual?
Here.
Yeah, no, for visual attack.
Oh, sorry, I closed it.
Yes.
Just give me a minute.
Thank you. Let's apply visual attack. What can we see? Ugly Britney. Yes? Yes. There are a lot of areas with high entropy. Okay, and we should use such Python script for extracting payload. Voila, payload. If you open it, what can we see? Do you have hex editor, hex view?
No, I don't have it.
What is it? This is MZPE file, and it is malicious file. We guarantee it. Yes, this is malicious file. Okay.
Now let's
My
try to
mission
make the conclusions.
completed.
Thank you, Evgenia. It's my
You're
turn.
welcome.
So, it is sure that we definitely need to detect steganography in the security suites, and not only in the security suites, because this technique becomes more and more popular among the malware offers. And currently, security suites, I mean anti-APT products, can do almost nothing with steganography. There are ways and methods how to detect it, but we tested and implemented some of them, but there are things to be improved. And of course, we understand that this is an our cat and mouse game, of course, but this is our job, it's our work.
And
It's
we
our passion.
love our job. Yes.
Here are our email addresses, and if you have any questions, please feel free to ask us. Yeah?
Yes, please.
So the payload itself gets executed when clicking on the image and showing the image.
Excuse me, could you speak please a bit more louder? I can't hear you from this point.
So,
Come to us.
so the payload gets executed when the image is opened.
So, can you repeat please your question?
Yeah. The payload that is embedded in the image.
When you open the BMP file, no, of course. As you can probably know, BMP files don't explode. And you need something to extract a payload from a BMP file and then run it.
Okay.
Anybody else? Yeah?
What's the amount of information that you can embed into an image, for example, without modifying his original size?
Well, thank you for the question. It's a very interesting question. It depends on using 1, 2, or 4 least significant bits in every bitmaps. So if like 0T, you will use 4 least significant bits in every byte, then the volume of the container is 1/2 of its size.
1/2 of the original file?
If
I'm not sure if I understood. You can embed 1/2 of the size of the original file?
yes, it's true, but only in case when the malware authors use LSB steganography by modificating 4 the least significant bits in every byte. Byte consists of 8 bits, and 4 is 1/2 of them. Yeah?
Would you publish your scripts?
Not yet, because we are going to implement this logic in our anti-APT product in Qatar. It's a commercial product, but maybe later when we will do some some job to optimize to speed up my script, then we will publish the original one.
And I've been trying to invent things how to hide information in different formats. How much that does detection depends on the knowledge of the format? Because, for example, you found the extra information because it differs from the typical data that is in that kind of file. What if someone hides information with the same kind of, it depends a lot on the characteristic that you find to differentiate the
So
good data from the
from-
bad one. How much, summarizing, how much does detection depends on the specific format?
Of course, it depends on the specific format because you definitely have to know the file format to analyze it. Actually, I've seen steganography even in plain text formats by adding additional spaces. Is it all? Thank you.
Thank you.
Sergey, it's your turn.
So thank you very much. It was so interesting. I'm sure we will get the slides so we can distribute it. And now it's the turn for Mr. Janikowski, who's also from Kaspersky and working on malware analysis.
Ты не можешь помочь. Ты если мне ответишь, нахуй, ты мне про этот инструмент рассказал. Wait a second. Okay. Yes, yes, yes. Выскажи. Раз, раз. Как меня слышно? Раз. Окей. Paul, where are you? We need to start? Can we start? Okay. Okay. Oh, it doesn't. This one. Okay. Okay. Hello, ladies and gentlemen. My name is Sergey Yanakovsky. I'm malware analyst in the anti-botnet unit of Kaspersky Lab. I'm going to be here at the Overdrive conference and have a chance to tell you about our work as an anti-malware research group. The theme of this lecture will be mainly DNS tunneling, but that's not all. I would also like to tell you about the alternative means of communication, provide a short historical overview of them, and share a few thoughts with you about the future of malware. Firstly, like any other area of computer science, malicious software continues to develop thanks to it being a favorite of cybercriminals, due to its earning potential. In addition, like any other evolving species, its main attribute is communication. When we talk about communication, we mainly mean data exchange with the command and control server of the intruder, not between infected hosts. From Morris Worm to Zeus banking triumph, malicious software has been on a long journey, and we have witnessed beautiful, strange, and sometimes slightly stupid ideas from virus makers when it comes to the CNC communication. On this slide, you can see a very basic division of the most popular ways of malicious communication. They have been divided according to a simple criteria: Is it stupid or not to implement them in malware? Protocols based on plain text data exchange is a bad idea, you know. It's hard to extend their functionality, it's easy to analyze and detect them. And as for me, I'm tired of reading the messages of botnet owners within CNC commands. Within CNC commands. Many of them like to use the control server with thousands of infected hosts like a normal chat, as we have seen with Mirai and Archive botnets, both built over IRC servers. In contrast, the use of structural protocols like JSON or XML with a good encryption or a custom binary protocol is a good idea, you know, and usually makes our work more complicated. Here's on the slide you can see a good example of one of the latest modifications of Zeus, named Teradot. It uses a binary protocol named UCL to pack required variables in a packet, backSOR and RC4 for encryption. It uses the same algorithm for downloadable models and web injects. And its main purpose to steal a user's money by accessing account information while they visit bank web pages, just like most modifications of those. It can extend and change its functionality and can be hard to analyze it due to high level of protection it possesses. And here's, you can see 2B packets transferring data as is without encryption or encoding. 2B is Trojan, which can steal money from commercial organizations by substitution receiver credentials inside simple text files, which used by 1C software to exchange information between databases and banking clients. 2B used the UDP protocol to send various pieces of information to the command and control server, like amount of money to steal, for example. The CNC address can be stored inside and resolved through any of these protocols. You can use namecoin to avoid buying vulnerable, Tor to stay anonymous, or P2P if you think that's a real good idea. The domain generation algorithm is a classic, of course. Integer variables and initialization variables stored used to initialize pseudo-random number generator are stored inside the malware and used to create a set of possible domain names. Okay, now, if you think for a few minutes about all this malicious data circulating through networks, what's it? 1, 2, 3. 1, 2, 3. 1, 2, 3. You can hear me? Okay, okay. If you think for a few minutes about all this malicious data circulating through networks and infected hosts, you will understand the main problem with both groups of protocols, stupid or not. They're too obvious. For example, when you see low entropy data and plain text headers inside the traffic dump, what it can else be like not malicious traffic. Yes, sometimes even normal software uses such features, but not so frequently. We found a lot of, we found many new malicious families without reverse engineering the original samples by simply checking the traffic, traffics from sandboxes. Now we have finally approached the main theme of this lecture, then a stunning and the alternative means of malware communication. Firstly, I would like to tell you the first story which I ever heard. First, I would like to tell you how it was in the good old days. When I first got into the informational security, the first story which I ever heard was about the malware transferring data using the Skype voice channel. Of course, the idea of hiding messages in less significant areas of signal or in noises is very old, even older than computer science. But in case of Skype, it was really cool because Skype was a very complicated program with a bunch of anti-reversing and anti-debugging tricks. For example, it refused to run on the same system with kernel-level debuggers like SoftEyes. Therefore, the development of such complicated malware requires a lot of time and knowledge. So the idea was cool, but not very popular due to its complexity. On this slide, you can see an example of the message encoded into the voice channel. Of course, in the case of Skype, it was very different, but the technique used was the same. Just wait a second, please. No sound. Okay, strange. Okay, thank you. Okay, please listen to this. At the end of the presentation. At the end. I already prepared a song. Try to increase the sound. I don't sure that will help, but we will try. Russ, 1, 2.
Okay, look, we both said a lot of things that you're going to regret. But I think we can put our differences behind us.
Do you hear anything? Just a little, okay. It's just a few words of gliders, nothing more. Now try to identify the external sounds, noises in the same recording, but with the encoded message.
Okay, look, we both said a lot of things you're going to regret. But I think we can put our differences behind us.
If you have a perfect pitch, you probably noticed few new noises at the beginning of recording. The WAV audio file format is very simple. Just a few attributes and the sound data represented at frames size of 2 bytes in this example. To encode the message, I just calculated the average value of frames at positive X, and replaced few of them with large number, adding individual characters from the message. After you receive the message, you need to find the values above the prefix, larger than prefix, and decode the message from it. I use a very simple algorithm, and you can easily improve it to remove any noises or make it much more effective. You can find its source code in the bottom by following the link in the bottom of this slide or in the lecture materials. Skype audio interception was cool, as I already said. Cool idea, as I already said, but complicated. The understanding by comparison is very simple and stealthy and stable technology. For example, your network administrator can configure a near-perfect firewall but how can he block DNS requests to the Google server? Alternatively, if you are not very attentive analyst, you can even miss it in open Wireshark traffic dump. So how can you care about DNS requests? On this slide, you can see a general representation of DNS tunneling. Firstly, the malware creates a DNS request to the Google server in attempt to resolve the address blue.old.new, whereas old.new is a real host with an IP address, and the blue part is just a beacon for the command and control server. Google knows about old new, but it has but it has never seen the blue one. So it tried to check the 53rd port of old new host to see if it has an upper level domain blue old new. Our host, our CNC server doesn't have such, but since the CNC server, it replies with some binary data, which represents by Google like an encoded IP address, but in fact, it's a reply from the CNC. Because all data going through trusted DNS server, we also can name this technology like DNS proxy. We first detected in the wild with the help of generic snort rules. Snort is one of the oldest technologies to detect malicious traffic. Snort, various software has been created with help of this technology. Snort provides a flexible inner language for implementation required match conditions based on regular expressions and byte patterns of any data associated with the packet. After the first encounter, we improved the detection and named all malware which use DNS proxy or DNS tunneling, as you want, like DNS, in tune with the name of the original DNS protocol. The first example contains a simple backdoor which provides a set of most popular functions of this malicious family, malware family. File system manipulations, file downloading, command executions, and so on. It uses a base 64 for communication and simple binary protocol for replies and requests. At this slide, you can see the initial packet structure, which contains information about the infected system. After the first request, the command and control server replies with both Unicode ID and continues to communicate with it using short commands. With help of improved detection, we found nearly 20 modifications of DNS tunnel which have been used by malware. As you can see on this, here's just a few of them. As you can see, some of them use encoding and encryption. Others just transfer the information about the system as a part of DNS request. Some of the samples were no more than test programs, but many of them were serious malware used by some APT actors. You can find traffic dams with examples of DNS tunneling by following the link in the bottom of this slide or in the lecture materials at the end of this presentation. I already told you about the past and present trends. But what next? The main duty of a security researcher is to think at least one step ahead of virus makers. And usually such predictions lead us to the threats which are already being used by intruders. Therefore, I tried to imagine new alternative way of communication. And I got thinking about one of the most popular trends of this day. Hey guys, do you ever heard about cryptocurrency? If you are not, you probably don't spend much time in the internet. We are not here to talk about Bitcoin, but about its youngest brother, Ethereum. Here's just a few facts about it, just in case if you never heard about it. Firstly, full description of Ethereum blockchain will take much more time. Firstly, all transactions are stored inside database represented here in a set of blocks, which you can freely download and read, but can't change except the last one. Each block connected with previous one and the next one with control sum. Secondly, each transaction contains two variables, two attributes, cryptocurrency and gas, which represents how much you want to pay for any operation in an Ethereum network. Gas is cheap and you can set whatever value you want above the limit for current operation. All unused gas will be returned to your account. So you can think about gas like about buying a process time in a distributed network. That's all about my little facts. Our target is a command line interface written on Golang, a very popular and interesting programming language. There's also implementations on other languages, but they're much less popular. Golang GET not only enables a connection to the Ethereum network, but it also enables all possible manipulations over it. To form the transaction, you can use the interactive console to implement the transaction in a JSON-like form. After that, you need to execute the command and pass your account password to it. And after that, your transaction will become a part of a new block, which appears on blockchain within 15 minutes, or you can do it even faster by yourself on dev mode. Yes, GET allows you to deploy a local Ethereum network for development purposes or just to play with blockchain. Transaction has a field inside packet for any data you want, but it's too obvious to be used by an intruder. Therefore, the idea is that we can encode whatever information you want in a gas field. As I already said, all unused gas will be returned to an infected user. And as a result, you will have the required information in a public data storage with no need to access directly to an infected system. How is it done? Nothing special, just few old techniques like remote heap allocation and small modification of the required code. All these little tricks are implemented into a library named Eternaris. You can find its source code and Eternaris, yes. You can find its source code and compiled samples by following the in the bottom of this presentation or in the lecture materials. We need to intercept the execution of the send transaction function. You can see its full name on this slide. By replacing all underscores with dots, you will get its full path from official source code on GitHub. If you ever had to deal with Golang, you probably know that it's possible to restore the function names inside them. I'm not very familiar with Go compiler, and the only way to locate the required function, as far as I know from a Red Naga security article, is to parse a special section of a file. Get doesn't have such section, so the simplest but not the best way to locate the required function is to read executable section and search a byte pattern of the function start, which you need to find. If you know how to do it without a pattern search, please write me an email at the end of this presentation. At source code, the send transaction is implemented with 3 arguments, where the second one is arg object, which contains information about the transaction, already spoiled from inconvenient JSON form and encoded to an easily to change binary one. If you try to debug get and go to the send transaction routine, you may see that arg object is passed as third one, not second. But this is just because that in Golang program, the first argument is always an associated pointer to object which contains current routine. Just never mind about it or any other strange variables and structure you may see. We are here not to talk about the Golang mechanic, but about the future of malware tech. Sliding over top of the stack, you will reestablish the structure of encoded JSON data, just like I do. Here on this slide, you can see a treasure map pointing directly to the required guess field. Once you change it with whatever you want, you will include required information into the body of a newly created block. The way we do it seems similar to the way of encoding messages in the voice data previously mentioned. Ternaries contain simple payload to be written to the get program with only one function on the board. It will always change the value of guess field to the fixed number, which represents in hexadecimal form as beef. Here you can see the comparison between the original send transaction routine and the patched one. When the execution flow comes to the send transaction, it will immediately jump to the remote heap, where we can do whatever we want with transaction data. After manipulation with it, we need to execute the commands from the function start and jump back with the same opcodes which we used to get heap. Here you can see the command line, you can see the screenshot of the command line interface of the get program. It's already infected with the ternaries payload. And as you can see, our little beacon is working as it should be. Message is created, sent, and will be delivered to any part of the world. you can use various software and script to parse blockchain and to locate it. Of course, the described protocol includes few very specific conditions. The infected system must already have installed the GET program, and users must carry out transactions from time to time. But all the way through, it's still easier than using the Skype voice channel as communication, for communication. In conclusion, I would like to say that regardless of future inventions in the malware software field, any serious threat will be always based on two main attributes. It must be simple and stealthy. Just never mind what exploits it includes, what algorithm it used to obfuscate code or targeting. If it can be efficiently used by an intruder, it's just another funny poke or experiment. That's all.
Thank you very much. Now we will stop for about 20 minutes to do a small break, and then we will be back with Ernesto, who will talk about modifying firmwares on microcontrollers to, in general, hack things, as we have been doing all these days. And for our speakers, we have a small present for you. So if you follow me or some of members of my team, we'll go there.
gracia enseñaros una ventana minimizada. Desinstala el antivirus, por no cortar el vídeo, luego se tira un rato con la ventana de que ha finalizado y le dice que no quiere reiniciar, porque aún nos queda la parte interesante de meter el script de bajada del archivo con el malware. El malware, de hecho, cogimos un crypter de unos archivos que tenemos de muestra en la oficina y dijimos, ¿cuál es el que detectan todos los antivirus? Y muy rápido, este. Pues ese. Entonces le dice reiniciar más tarde, lo decía, un tabulador, 2 tabuladores, 3 tabuladores, enter. Pasa lo mismo con la ventana de PowerShell, podemos ejecutar un PowerShell en background o el CMD o lo que queramos, pero lo interesante es que lo veáis, lo de que se puede ocultar una ventana ya lo sabe todo el mundo. Genera con un eco el y reinicia la máquina. No tengo muy claro por qué me ha salido el mensaje, pero bueno. Entonces, una vez reiniciemos la máquina, ya vais a ver, como digo, no me gusta nunca trucar nada de los vídeos y por eso sale también todo el Cam Studio y demás, para que se vea que la secuencia es válida y que no hay ni trampa ni cartón. Pero bueno, y además porque no me apetece. La cosa está en nosotros iniciamos el sistema, lo ejecutaba, pero claro, no podía poner el Cam Studio a grabar. Es que yo lo de la edición de vídeo lo llevo muy mal, ¿vale? No es una de mis... Entonces, lo que hago es enseñaros que efectivamente en todos los programas inicio, ha generado el fichero .bat y le ejecuto a mano, no pasa nada. Lo mismo que sale cuando lo inicias. Y efectivamente aquí vemos que ha ejecutado el comando de PowerShell, import module, y que se ha bajado sin problema el archivo. Con lo cual, igual que se lo ha bajado, lo puede ejecutar. Lo que pasa es que es un crypter, no tenía mucha gracia, pero podíamos haber bajado cualquier malware, porque esa máquina ya hemos anulado las contramedidas. A ver, un momentín. Bueno, hemos hablado en todo momento de emular un teclado, porque además es un dispositivo fácil de emular, pero Bad USB al final es, vamos a hacer de hackers, que es lo que somos, con un USB. ¿Hay más? Sí. Sami Kamkar presentó en 2016 Poison Tap, que con una Raspberry Pi 0 lo que hace es identificarse ante el ordenador como una tarjeta de red. Además, una tarjeta de red que le da al ordenador por DHCP todo el rango de direccionamiento. O sea, le dice desde la 0000 hasta el 255, 255, 255, soy yo la puerta de enlace. Con lo cual el ordenador, incluso estando bloqueado, y esta es la parte divertida, coge todo el tráfico de red y lo enruta para la Raspberry. Con lo cual ahí ya tenemos todo el tráfico de red. Si le ponemos una Wi-Fi o la 0 que lleva Wi-Fi, lo podemos enrutar hacia otro sitio, con lo cual de cara al usuario es transparente y tenemos un man in the middle hecho por hardware. Podemos capturar todo el usuario, podemos capturar las cookies del usuario, podemos hacer que binarios que intente bajar el ejecutable, sustituírselos por otros. Bueno, esto ya, como siempre, las maldades y lo que cada uno piense, es infinito. Está muy bien Poison Tap, no Tap, pero bueno. Dista de ser una herramienta sencilla y de botón gordo. O sea, es una prueba de concepto para ver que funciona y ahí hace falta meterle mano para que funcione bien. Si alguien se anima a seguir jugando con él y tal, yo lo animo. O sea, es una herramienta que yo creo que tiene muchas posibilidades y está ahí. Agradeceros a todos un montón haber venido, al equipo de Cyberweek por haber organizado esta semana que ha sido muy intensa para ellos, seguro. Al equipo de Phoenix Internet Security por la parte del ovipositor y que les doy bastante guerra para que hagan cosas. Al equipo de Vector Cybersecurity, que es donde yo trabajo y bueno, está por ahí Iván. No sé, no lo veo. Hola. Y darle las gracias a Dastra, a Dani, que también dio una charla anteayer, me parece, En su blog de HackerWay hay un par de artículos que hemos hecho con Joel, con otro compañero de Vector, hablando más de BAD USB. Hay una explicación sobre BAD USB de €1 y alguna más de todos los demás, con acceso a todo el código fuente, a los repositorios de GitHub y demás. Bueno, y a mi correo electrónico, contacto, Twitter y todas estas cosas. Por si a alguien no se le ocurre la pregunta ahora, pero se le ocurre alguna cosa mañana, pues puede entrar en contacto conmigo y preguntarme y decirme: oye, Ernesto, que se me ha ocurrido tal cosa, ¿qué te parece? O me he atascado, o creo que el artículo hay algo que no está bien explicado, pues sin problema. Para eso estamos. No sé por qué se duplica eso. ¿Preguntas? ¿Preguntas, sugerencias? Fruta podrida, ¿no? Por favor. ¿Nada? ¿Nadie se anima? ¿O no se ha enterado nadie de nada o lo he explicado muy bien? No lo tengo muy claro. Bueno, pues muchas gracias a todos por venir y por escucharme y espero que os haya gustado. Y si alguien quiere ver los cacharrillos, pues puede venir sin problema. Muchas gracias.
Gracias a ti por venir, Ernesto. Nos ha gustado mucho.
Lo quito, espera. ¿Cómo he ido de tiempo? Que es lo que más me apura, porque nunca les mido el tiempo yo a las presentaciones. Interesante, ¿eh? No, antes. No tenéis aire acondicionado aquí, ¿eh?
Necesito el ordenador. Bueno, ahora me conecto al Dropbox y creo que lo tengo pronto. Dani. The screen. ¿Es el titular?
Allà.
Ah.
I ara,
Yes.
5 segons.
Ara faràs la xerrada, no, Pau?
Ara fas la xerrada.
Ara quan ho fem els dos, no?
No? giờ giờ ông tiếng mà nhiều phần thì cái giờ thay về cho hai đứa các bạn để tiếp
So, do you hear me? I guess yes. So the next talk will be by me as a representation of, no, this is not working. Now? Yes. So we will wait for this screen to work. And the next talk will be, as I said, by me. In representation, I wanted to represent in some way, and not only to the general audience, to all of the people who's watching through internet, but also to all of the people, our speakers, people who came. This is our particular way to show you what are we doing here in Girona. What I expose here in my paper, it's not only the work that I've been doing, but it's also the work of my team has been doing with me, and my coworkers have been doing, like the people who are here from Surveys Web. So it's like a way to show you what we do in Girona in terms of cybersecurity research. And now, I don't know which button is. I think it's F something, but I'm not used to it. Nope. Well, I can do it this way. It works. So this talk is about designing network security architectures, or general network architectures applying security. So what does it mean when we talk about the network architecture? Are we talking about really basic things? Are we talking about complexity, about the loads of services, and so on? Well, a network architecture, we can build it from small networks, from small local area networks, to huge data center networks. In this talk, I will focus on large networks, like the ones you can have in a data center for a large company, or a hosting company. So that means we have networks with a lot of services running on them. Services from really small web applications to complete DNS services, etc. And we will talk about ways to do security on that things, so know what that actually happens on that networks, do analysis on problems, design incident response, and in general, make sure that the service is available the most of the time. So when we talk about network architectures in terms of security, we don't mean only security as the thing that I don't want to get attacked. For me, from my point of view, security is also availability. So if you have a service, you want your service to be active most of the time, all the time if it's possible. So stability and well-design of the network is important. I thought about key factors of when you have to consider when designing actually a network. So the first key factor may be service availability. So if you have a web page, if you host web pages for your clients, they have to can access to that service anytime. If you run an online shop, you will want your clients buying all the time. So your web has to be available, your mail servers have to be available, and so. Then, network availability. Your clients have to get the chance to access, but also your IT personnel has to have the chance to work on the network. So if they are going to move some files, some program to production, if they are going to work, connect, to administrate some server, they need to access anytime. Then it's information integrity. If you run a database, you will want access control, which is the next key factor. You want your data to be protected, not accessible, and ciphered, so encrypted. So if someone is attacking your server, they won't steal all your information. I've seen large databases of millions, even millions of registers in plain text. I've seen a lot of passwords in plain text in different servers. And some of them were in really important servers. I've seen a lot of sensitive information unencrypted on databases, and that's so sad because a lot of things that are done for protecting networks and machines in general are so easy to do, but people don't think about that sometimes. And then the last one is incident response. Security is not only about protecting. You have to think, you have to have in your mind that in some way your machine may break. Someone may steal your information. You have to have a plan on it so you can perform a response when something really bad happens. And we will start now getting technical, talking about these aspects. We will be like in a trouble to design all the architecture of a network. So from moment zero to a complete network. And I will focus on really important things or things that I think that some people may not think on first time, things that may be interesting, and some of them simple. First of all is network segmentation. Imagine you have a data center with a lot of machines, large data center of 3,000 machines. I've seen in a lot of places, a lot of machines, a lot of networks, when all of the machines are seeing each other, you can ping to all of the machines on the network, and etc. So if you have your web servers, just put it in one separate network. If you have mail servers, then they may go to another network. So the rule is so simple in that case. Think about all the services, all the machine servers you have, and then think, this machine has to be in touch with this other machine. Does this service or this machine or computer needs to interact in some way with this other? And if the answer is no, then use VLAN, use subnetting. Then make sure that these machines are not accessible in each other. The rule number one in designing security on a network is to limit everything. Do only what is necessary. If you only need to show static content, why do you have to install WordPress, for example? Don't add extra content, use only what you need. And in terms of network, do segmentation. Segmentation using VLAN technology, for example, helps us a lot, and using subnetting as well. One concept is using what we call DMZ networks. So in here you can see it. It's so easy. There's the internet, and there's the main router of the company. It used to be, depending on the company, but on the largest networks, really high powerful devices with a lot of throughputs and load balancing and so on. And then you have a separate production network. This network only has like really 2 or 3 services that have to be accessible to internet, maybe the company website or wherever. And then you have the internal network. And from the internal network, you don't have to all machines, they don't need to have access on the production network and so. So if there's some kind of incident on the working office network, it may not affect the production network. It's a really easy concept. Then there's a kind of design that I tended to use on designing security on large networks. Then you have ISP, what they call ISP level firewalls. For example, if you are a lot of days, a lot of companies have a lot of denial of service attacks and so. So if you start thinking about it, that's one thing that happened where I work. We had a lot of denial of service attacks on our network. And we started to analyze the traffic, to try to figure out what was happening, and a lot of denial of service attacks were due to bad malformed packets. So depending on your ISP can filter a lot of traffic that comes to your data center. So if you can do it, do it. If you filter, try to filter on the higher level of the network. So try to filter the traffic as soon as you can. And then, for example, filter or layer 3, filter malformed packets on the top of the network, and then you can try to apply custom layer 7 firewalls on almost the machine level or at least on the subnet level. So for example, you may have a web application firewall really close to your web servers, and then a filter for malformed packets on the top of the network, on the entrance. And that's it. And then, of course, you can also use local firewalls like IP tables and so on. Then, of course, if you run critical services like a database with all of the secrets of your company and so on, ask yourself, do these have to be connected to the internet? Is this have to be accessible through internet? Well, maybe not. So you can run this in a separate machine only accessible from your office network with a custom user for only one authorized person or something like this. And then, of course, to make sure that you always have the best availability, your network is available all the time, use load balancers on the top of your network and on your critical services. But of course, the thing that you have to watch first is the top of your network. So on your router, make sure that it has some kind of load balancer and so on. But also depending on the traffic you have. Then we will start entering some kind of some more in detail. Defense architectures. These are the advices that I tend to give when designing security. Of course, avoid common ports. I have this custom web application, has to be accessible through the internet. You know that if you use the 80 port, for example, for a web application, you will get a lot of traffic from bots. Once you connect a machine through the internet, you are literally bombed by bots. So you can just start moving it to port 8081, for example, or something like this. Then, if you have a really, really critical service you have to get on the internet, you can use some kind of technique like port knocking. Port knocking is a technique when, like, I want to connect to this application on port 8081, so I use port knocking and I first send a packet to port 70, then one other packet to port 24, and then some other packet to another port, and then the port 8081 will open for like one connection. You can use it, of course. Then also one thing that I used to recommend and implement is to use white lists. whitelists maybe a lot are a lot better, more better than blacklist. Whitelists, the concept is I only connect to this server from Girona, from this IP address. So I will allow only this IP address to connect to the network. Do I expect some of my workers connecting to my server, to my web panel, for example, from China? Do I have some workers or clients there? No, I block all the traffic coming from that country, or even I allow only traffic coming from these 10 IP addresses that I know, or these ranges, IP ranges, for example. Of course, you can use also blacklist, but I recommend whitelist for that case. Then, as I told, network segmentation is a useful resource. Also, if you can avoid user and password, you can also use, for example, some other things like crypto keys. You have an SSH server, and that has to be accessible for only one employee. You generate one SSH key, you give that SSH key to your employee, and then he or she uses that key to connect it. And then you make sure that you will only accept connections from that machine, for example. Of course, there are a lot of tools. If you have to use user and password, like fail2ban. Fail2ban is a tool that allows only limited tries of user and password. So you may allow only 3 attempts, and if someone is trying a brute force attack, fail2ban will ban that IP address. Use cloud technology, I recommend for your critical services. You can use virtual machines for your services. That will help you to perform snapshots or backups so easy and fast. And it may help you to recover and restore if some kind of incident is happening. Also plan backup and disaster recovery policies. Make sure that you know your network, you know the usage of your network, which data, and the time periods that your data is being written. So if I have a significant amount of information, of new data each week, I will make sure that I have a new backup each week. If that happens each day, I will do that each day. Then, of course, password, access control policies. Make sure you have all your software up to date, but also be aware of non-stable versions. And if you have red and blue teams available in your network, that will also help a lot. Blue teams test security, red teams test security in an offensive way. Blue teams apply patches and respond to incidents. And for data consistency, also make sure that all your servers, all your machines and everything is well protected, but also on the physical level. So you can use right technology for making your systems some kind of tolerant to failure. And there's also a lot of tools like Bacula, for example, for performing backups. We've been using that. But you have also other tools for disaster recovery. I recommend DRLM project. This is made by some of ex-students of this university. So you can search for internet, search in internet for it. And I will start entering in more details and more custom things that we've been doing in our company. So then you have a well-designed network in some way. You have some segmentation, you have some good policies, and so on. But you also have to know that attacks will happen on your network. In some way, you have to be prepared for setting up
malware analysis team or a computer security research, call it whatever you want, but you will be bombed by malware on your mail servers. Attackers will try to break into your systems and upload content and so on. One thing that is interesting to know is that what is happening on my network? What is people trying to do or bots trying to do on my network? And a good method to try to figure out what's happening is the usage of honeypots. And there are, I classify them into sections, research honeypots and defensive honeypots. I've been using both. Research honeypots are the ones you use as some kind of sensor to attract attacks into them, and then just study what kind of attacks you are getting and try to learn from that, so you can design better policies and be focused on certain things on the future. And then there's defensive honeypots, who are mainly used to distract the attackers and make them spend time and use that as an alarm, some kind of alarm on what's happening to your network. So yeah, first one, you have you can check and use Honeybee, which may be used as a defense honeypot. So you put a defense honeypot just as a regular server. So you have in your network, for example, a web server, a mail server, and then you have this defensive honeypot. And a defensive honeypot will emulate a normal server. You can just open and listen to which port you want. You can start opening a lot of services, a lot of IP addresses, listening on a lot of ports. So if an attacker is scanning your network looking for some entry vector, they will start seeing a lot of services, and then the attacker will have to figure, what can I do now? What do I attack? Why there's 50 machines? Which one is good? Which one is bad? And if you know that some of these machines is being scanned, you will be like, okay, this is a fake service. Someone is trying to attack a fake service, so someone may be trying to attack my network, and then you can respond. And then you have, on the other hand, research honeypots. I've been using them as sensors for looking what happens on my network and building policies and research based on what I capture with this. So I've been using these honeypots to get threat intelligence. For example, you have an example. You set up a honeypot with simulating a FTP server, for example, and you collect all the passwords that are being tried to that server, and then you make a huge dictionary with all the passwords you are capturing. So you know that these passwords are the ones that attackers are trying to use to enter to your network. So then you run a dictionary attack to your own network and see if someone is using some of that password, and if someone is using some of that password, then you just go talk to them and make them change that password. Also, you can integrate, I've been integrating this into a system when our users, when they create their password, the system will go and check with that dictionary we collected with this, and then the system will tell the users that, okay, your password is good, or your password is being used by attackers, so don't use this. I've done centralized system. So what I exactly done here is I set up a lot of honeypots, different honeypot sensors, and then open that to the internet. I looked for attacks on the SSH protocol, on web applications, on MySQL and Microsoft SQL servers, Samba, and yeah, that's it. So I collected a lot of malware, a lot of URL attacks like SQL injections, even some exploits, a lot of WannaCry ransomware, and kind of samples. And then I centralized that into a platform, and that platform does a lot of things. For example, one thing I do is I collect all the malware, and then I hash all the malware. So if some attachment on our web servers match with the hash that I collected, then it gets blocked. But I also use Kuko Sandbox, and I move all the malware using the Kuko API to run the malware in the sandbox, and basically I centralize and automate analysis on that malware. I will talk about this. And this is some example of the things that I find. You get a lot of attacking systems trying to look for something, some special URLs. For example, they look for file uploads, for SQL injections, for some backdoors, and these kind of things. On the other hand, I get a lot of IP addresses of attackers, so I blacklist these IP addresses from my production machines. Then I move all the malware to sandboxes, run automatic analysis, and so on. So you can do a lot with this. And if you write custom honeypots, you can even do more. Then when you have a general security on your network, and you know what do you have and what they are trying to attack, you can move to protecting specifically what do you have. So, for example, you can have web servers and mail servers. And when protecting mail servers, you can use postfix and Dovecot, for example. You can use high availability proxy to do some kind of load balancing between mail servers. Of course, you can also apply things like spam assassin and clam antivirus to some kind of basic spam avoidance and to watch for a virus. Clam antivirus is so basic, but you can also combine it with other systems or implement Yara rules, and that helps a lot. Of course, enable encryption and disable anonymous login, and limit the number of connections you have to avoid some kind of dictionary attack and so on. And make sure you have at least 2 MX records in your DNS to avoid these kind of failures that may happen. I already talked about Kuko Sandbox, which is so useful in our company network. We have a lot of mail servers, a lot of mail coming in and coming out. So one thing I do is make some kind of script program that is extracting all the attachments on the mails, and using the Python API of Kuko, run every sample, extract every sample and run it into a sandbox, and then collect information about it. So then the blue team can go, check what's in Kuko, check all the logs, and try to figure what kind of malware are we having. Are we having some kind of custom attack from one place, and so on. The algorithm is written here. So in the mail queue, you check for mail, Does it have an attachment? Yes, we are extracting that. We even can use some kind of fuzzy logic to if you have some kind of alarms in your sandbox, automatically send a mail to the user like we may have detected a malware or some suspicious file in your mail, check your security, etc. Or inform security teams. And with web servers, you also can do a lot of things. And yeah, you can, of course, first of all, know your traffic, know your hardware. As I said before, if you only have traffic and you run a shop, you only have traffic from Girona and Barcelona, be careful if you see something coming, a lot of connections coming from other countries, because you may be under attack, some kind of botnet and everything. You also can do load balancing. You can do cache for accelerating connections and so on. High availability proxy is a nice tool to use for doing this load balancing. And of course, you can protect web applications. I recommend mod security of Apache. Lance was talking about that in the workshop. So this is an example of a log of this mod security plugin. It's like a module of the Apache web server. So here, for example, we see an SQL injection attempt, and we have all the log here. So if you use mod security and it's basically configured and you have it up to date and everything, if an attacker is trying to do some kind of SQL injection, as Davis showed us yesterday, you will get some kind of log and you can block connections and everything. And then, yes, you have to protect custom applications. So, for example, what happened to me when defending a large network once was like we were talking with the developers and the network engineers, and they told us, okay, we have this legacy application. This application is so old. We've been using this for a lot of years. This is from 2005. It's really old, but we can't switch. We are not able to switch to another application to make a better application to fix security and so. So what do we do? It's easier to pay to someone to build security around this application rather than build another application. So in that case, I was like, okay, it's time to be creative. What we've done was we've done an analysis on that application. That application was a framework with a web server. So after a quick analysis on that application, we wrote an exploit for that application. And then, I think, yeah, we wrote an exploit. This is actually the exploit we wrote, some of the code. And with that exploit, we've done an analysis. We extracted a pattern, like we've done an analysis, basic analysis with Wireshark. So we extracted a pattern of the exploit, some bytes, significant bytes, for identifying that. Then we built snort filter for that exploit, and then we released that exploit on the internet. So we knew that all of the attacks we will be getting may be from the exploit we just released. We already know our exploit. We built a filter for our exploit. So, in fact, we got a lot of alerts by time about people using the exploit we wrote and we released based on what we've done. So we've done some penetration testing on that service, and then we built a filter based on what we found. That's part of the filter. This is so basic. In fact, this is only looking for knobs on the content, but you can figure out what we did. We did an analysis, and then we make a filter, and then we get some alerts. Also, finally you can move to the operating system level. So you have a well-designed network, you have high availability, you have nice protected web applications and so. But what happens on the operating system level? And yeah, people may enter sometime. Attackers may enter to your system. So you have to be ready. One thing that I recommend on the operating system level, aside from enabling user access control, permissions, so groups and users and everything, and also kernel security modules and configurations such as address space randomization, stack protector, etc., is checking what you actually need and what you actually use. So if you only use Apache web server, if you only use postfix, allow only these applications to run. Don't allow any kind of application that it's not meant to run on that server. So if you are running a web server, why do you need to run some kind of file in /tmp directory, for example? Focus on what you need. And of course, you can use a lot of models. I wrote a small program which acts in some way as IP tables, but at the operating system level. It's based on a kernel module that patches the kernel in some way and runs some kind of hijacking on the exec system calls. And then every time a new process is about to execute, this module monitors that process, performs a check, and then if that program is allowed to run, then the module lets the program run, and the program executes, and a new process starts for that program. So I use that to let only allowed programs to run on the server. So I said, like, okay, we are only running Apache and these other 3 programs. That's what we need. We are not running anything that's not on this list, basically. I will release this during the next week on GitHub. And I also wrote a custom file scanner which was similar to Yara. I wrote that for learning, but I actually find that useful. So I had to manage a web server with a lot of files, so I started writing a program and running hash functions on each file of the server. So if something changes, I get an alert. If you have a static web page, if you have a web server which allows no uploads, then if something is changing, you have to be aware because it may be an attack. Also, you can use these solutions with along with other commercial solutions to complement it. And operating system security is an open source program. Also, you have tools like Alien Vault, SIEM systems, and you can centralize security alerts, predefined security alerts on what's happening on your server. And that's it. I tried to show what basic security was in terms of designing networks. In the future, I will enter in detail in some of the topics that I explained. And some of the tools I wrote, I'm about to upload them on GitHub. So if you're interested, just reach me and we can talk about it. And also, thank you to everyone for coming to this wonderful event we had. We will be back with more the next year. So stay in touch and we will let you know. Any questions? No? Thanks. And that's it. Also, thank you to all the volunteers and teachers at the University of Girona that made this possible. And thank you to our wonderful speakers we had this year. I really hope you to be back the next year. Thanks.
Он будет ужасно смотреться. Не делай себе. Вообще, нам, Жень, давай сама сообрази, как сделать хорошо, ладно? Ну, фоткай давай уже. Хорошо, с синим экраном сделай вот так как-нибудь, не знаю.